I'm waiting. Thank you. Right, so waves. Can anyone just tell me anything they can think of when I say the word waves? Yep. Frequency, excellent. Yep. Amplitude, brilliant. Did you say sound? Sine, oh yeah, very good. Yeah, sine waves, yeah, cosine waves. Yeah. Hertz, brilliant. Yeah, Andrew. Vibrations, longitudinal. So loads of brilliant words already. Probably you already know most of the first lesson that I'm going to talk about. So you did quite a bit of this if you were here in first year and you did sound. I know I taught some of you in first year. So you would have talked a little bit about waves already. So some of the waves that we're going to, some of the things that we're going to talk about today, the new things you've probably come across already. If you don't remember anything from first year, or if you weren't here in first year, don't worry because we're going to go through the basics, start from scratch again. Okay. So first page of your booklet, or the first actual page. So there are lots of different types of waves: water waves in the sea, light waves, sound waves, radio waves. Okay. And waves have certain common properties, and the important thing is waves transfer energy. Sound energy is produced by vibrations, which is what you mentioned, brilliant. And the number of vibrations per second is called the frequency of the sound. Okay, so you can work out the frequency of something if you know the number of vibrations and the amount of time it takes. Don't worry, we'll go through that equation again later. And it is measured in hertz. Again, all these things you've mentioned already. And tuning forks are used to produce a pure note, a sound with only one frequency of vibration. So basically a tuning fork, they vibrate back and forth, and different tuning forks vibrate at different speeds. So the more vibrations per second is a higher pitch tuning fork, and the fewer vibrations per second is a lower pitch tuning fork. And the higher the frequency, the higher the pitch of sound we hear. Sounds of a range of frequencies can be produced in the lab with a signal generator connected to a loudspeaker. Can anyone remember the range of human hearing from back from first year? 20,000 is the highest, yeah. And yeah, well remembered. So between 20 and 20,000 hertz. Okay, so humans have quite a wide range of hearing. So do we want to do, shall we listen to high pitch, low pitch, see who's got the best range of hearing? Okay. Okay, so I just when I did massive sound frequency, some of you are thinking, but basically what I do is normally I get you when I'm doing that at the moment. So what I do is I'll turn it up, okay, and I want you to put your hands up so you can hear it. So obviously, hopefully you can hear this, so you have your hands up, okay. As soon as you stop hearing it, put your hands down. We'll see who's the last person with their hands up. Can you also hear that?
So you're everyone was shut up. No. You can hear everything inside the focus. It's probably the lights.
So, we've got some people who've got a really good range of hearing, some people don't. Obviously, animals and things like that have wider range of hearing, like dogs can hear a higher pitch than humans. So the material through which a wave travels is called the medium, and sound waves need a medium to travel through. So they can travel through solids, they can travel through liquids and gases, but they cannot travel through an empty space. Okay, so if you put your ear on the desk and somebody knocks on the end of the desk, you should be able to hear the vibrations. Okay, right. So I'm going to use this equipment again, but what I have is I've got the loudspeaker facing this way for a reason. Because what I'm going to do is I'm going to light this candle. Okay. Now, hopefully, this is going to work. So, what I've got Alright, guys. Okay, so what I've got here is I've got a candle and it's you can loudspeaker there as well. And you can speak in the background. Okay. And if I turn up, sorry, turn it on, yeah, that helps. So you can see loudspeaker moving back and forth. So that's what's making the noise. Obviously, the loudspeaker is vibrating back and forth and it's vibrating the air particles next to it. And you can see the candle vibrating back and forth as well. I mean, I don't know the candle then. So, if I change the frequency, you go a bit faster. If I lower it, So you can see the candle is moving. Okay, so the next sort of part of the booklet says the following demonstration aims to help us understand what sound waves actually are and how they travel through a medium. The candle's lit, the signal generator is then set to a very low pitched noise and is produced by the loudspeaker when it's switched on. The low pitch setting on the signal generator causes the cone of the loudspeaker to move backwards and forwards a small number of times each second. So you can see there the candle is moving back and forth, sort of the same rate as a loudspeaker. So back to our notes. Okay, so it's just the thing that it sounds like. Right, so what happens to the candle flame? Moves back and forth at the same rate as the loudspeaker. Okay, and what's happening there is we don't have nothing in between the loudspeaker and the candle. We've got a lot of air in between the loudspeaker and the candle. So when the loudspeaker moves back and forth, it then moves the air particles next to it back and forth, which then move the air particles next to that back and forth, which then move the air particles next to that back and forth. So it's a big Mexican wave, but of vibrations instead. And when it gets to the candle, the air particles move back and forth and move the candle around. The candle flame behaves as it does because the forward movement of the loudspeaker cone pushes some of the air particles between the loudspeaker and the flame closer together. In fact, the vibration is called local increases and decreases in air pressure relative to normal atmospheric pressure. So, if you were all stood in a line and you're all moving back and forth randomly, sometimes some of you will be closer together and sometimes some of you will be further apart, just the way that vibrations work. Okay, so if that's going like that and that's going like that, sometimes they're further near apart, sometimes they're further apart. So when they are closer together, they are called compressions, and when they are further apart, they're called rarefactions. Okay, so here's just sort of a diagram of them. So when they've got lots of particles so close together, they're called compressions, and when they're a bit further apart, they're called rarefactions. So that's the kind of how waves work in a longitudinal wave. Okay, so compressions and rarefactions spread out as a longitudinal wave. Now, there's only at National 5 Physics, there's only one type of longitudinal wave that you will need to know, and that is sound. Everything else that you come across in National 5 is called a transverse wave, a different type of wave. Okay, there are other longitudinal waves, but you don't need to know them at National 5. Things like earthquakes can be longitudinal as well. But you only need to know sounds. Okay, so quite often questions ask you to clarify whether something's longitudinal or something's transverse. Everything will be transverse apart from longitudinal. Okay. Right. Waves on a blinky. Okay, so this is quite difficult to do. I'm sure I can get somebody up to stand 1 meter apart from me. But so waves on a slinky. I'll just have to hold it like this. Okay. So you can demonstrate longitudinal and transverse waves with waves on a slinky. Okay. So longitudinal wave, it goes back and forth in the same direction as the travel, the energy travel. So it's basically going back and forth like that. Okay, so we're going on, it's moving that way, and the vibration is moving that way. Okay. So longitudinal waves can be set up in the slinky, and what happens is when you have one end fixed, when you do that in that direction, then you end up with some compressed parts and some stretched parts. So you get the compressions and rarefactions in there. And the definition of a longitudinal wave is one in which the particles of the medium vibrate along the same direction as the wave is travelling. So if the wave is travelling in that direction, the particles are travelling like that. They're moving back and forth. Like one of those old school dances like that. So back and forth like that. Okay, so they're moving the same direction as the wave. So the wave's travelling that way, the particles are moving that way. Okay, so that definition is very important. You need to learn that. So I always put a sort of a love heart if there's anything you need to learn by heart. But transverse waves are what you would normally do like that. Yeah, so they move up and down. So if the wave is traveling that direction, they'll do that. Along that way. Okay. So transverse waves, here's the diagrams. A transverse wave is one in which the particles of the medium vibrate at right angles to the direction in which the wave is travelling. Okay, so they go up and down if the wave is travelling back and forth. So they do that. Whereas a longitudinal wave just does that. Okay, again, you need to know these definitions. And as I said, longitudinal waves, the only one that you need to know for National 5 is sounds. But transverse waves, you get water waves, light waves, gamma, you've done gamma. Also, radio waves. Quite a lot of people get mixed up between radio waves and sound waves. Radio waves aren't sound waves. They produce sound at the end of them, but the way that the radio waves themselves are different. Okay. Page, we will be doing more work with this ripple tank later in the course, but this is just an introduction to the ripple tank. So we can actually demonstrate waves on a ripple tank. Okay, so what is this thing? Okay, so can you see the back of it? Right, so what this is I can stick my hand through here. So what is, we've got this shallow amount of water up here, and then here is a mirror. So it's reflecting what's happening up here onto this screen. So you can see the wave. So this has just got like a little bar that's vibrating back and forth, and up and down even, and it's producing waves. So like waves if you were looking sort of downwards into the sea, instead of seeing the waves crashing, you just see sort of lines, the tops of the waves. Yeah, and that's what we're seeing here. We're just seeing the tops of the mini waves. Okay. What I can also do is I can grab some of this water, a little dropper, and then drop it. Okay. So like when you throw a stone into like a pond or something, you get the ripples going outwards. And what you're seeing there is you're seeing waves go outwards. You're looking from the very top. So if you were looking downwards, which is if you dropped a stone into a lake or a pond or something like that, you would see circles going outwards. Okay, so this is called a ripple tank. And yes, basically all you're doing is you're seeing the very top of waves that are produced. So this case is just flat waves. If you drop something in, and you can also put in like little obstacles, see what happens around them. And that's what we'll be playing with more later on is we'll be putting obstacles and seeing what waves do when you put obstacles in the wave of them. That's because you're opening from the top. But if you look side on, if you look side on here, you can see a little waves going like that. Right? So these are transverse waves, yeah, but as you said, they don't look transverse from the top. Okay, so that's ripple time. So we'll be playing with that again at some point. Yeah, push this slightly out of the way. Right, so there we go. We can see waves carry energy outwards from their source with no transport of the medium through which they move. So basically, the energy moves, but the medium itself doesn't have to move. You can, yes. Circular waves radiating out from a point source become weaker as their energy is spread over a larger circumference. So if you looked from the very top, you would see these lines. But if you looked side on, you would see the waves crashing. Yeah? But if you look from the very top, so if you were looking bird's eye view, you just see lines where the tops of the waves are. Same with this one. So the dot in the middle is where the first wave is, and then as it crashes out, they get smaller and smaller because of their energy, they're losing energy. And this one corresponds to this one, and this circle corresponds to this. So what you're seeing is the tops of the waves. Okay, so that's the ripple time. Now, describing waves. Some of you already gave me quite a few words that we're going to come across again here. But again, if you haven't heard about them before, no worries at all. So all waves can be described in the same way and have some common properties. Okay, so we've got a few things that we're going to go through. So the first one, a crest. So a crest is kind of what you might think it is. Crest is the top of a wave. So that's a crest. That's also a crest there, and that's also a crest there. And a trough is the opposite to a crest. So a trough is the very bottom. You might sometimes hear of a crest being called a peak as well. So crest is a point at the furthest distance up from the zero position. And this line here, the very sort of dotted line in the middle, that's the zero position. So a crest is the highest point, and trough is the lowest point down from the zero position. The amplitude of the wave is the maximum displacement of a particle, that shouldn't be there, from its zero position. So the amplitude is, and this one people quite often get mixed up with this, is from the zero position to the very bottom, or from the zero position to the very top. It's not from the top to the bottom. Okay, so it's either from here to here, or from here to here. It's never all the way. Yeah, and I can guarantee everyone will make that mistake at some point. And amplitude is measured in meters. The wavelength is basically the length of one wave. So it's the minimum distance in which a wave repeats itself. So it's from one point to the identical point, the identical next point. Okay, so this equals the distance between two adjacent compressions in a longitudinal wave, or the distance between two adjacent crests in a transverse wave. So the wavelength, the easiest way to see a wavelength is crest to crest. But you could go from this point here on that wave, you've done one full wave, and it's that point there again. Or you could go, if we look at this point, go one full wave, next point, and the wavelength is the distance between those 2 points. So it's the distance between two identical points, one on one wave, one on the next wave. It's given the symbol lambda, sort of like an upside down Y, and it's measured in meters. Okay, so we've got quite a lot of meters going on here, but it's a distance. The frequency, a lot of you already know a little bit about the frequency. So the frequency of the wave is the number of waves produced by its source each second, or the number of waves passing a point each second. And it's given the symbol F and is measured in hertz. So to find the frequency of something, you would count how many waves pass and divide it by the amount of time that those waves pass in. So if you had 2 waves in 1 second, it would just be, frequency would just be 2, so 2 waves in a second. If you had 4 waves in 2 seconds, the frequency would be 4 divided by 2, so 2. Yeah? So you can use that handy equation there to work out the frequency if it's not entirely clear, because it's not always clear in the question. The period of a wave is the time taken for one wave to pass, or for one complete wave to be produced, or for one complete wave to pass a point. Period is given a symbol capital T, and it's important that we distinguish between capital T and small t. And it's measured in seconds because it's a time. And period and frequency are closely related. So period is 1 over frequency, and frequency is 1 over time period. Again, just be careful that's capital T, not small t. So it's time period. It's very important that it's just the time period that you use. And the speed of the wave is just speed. So it's the distance travelled each second. So it's distance, speed. To work out the speed of a wave, you can calculate it using speed is distance divided by time. Just as you always calculate the speed of anything. If you had a person running and they went 5 meters in 10 seconds, you work out the speed of that. Okay? So, to practice those, there's basically this page that we've just looked at. You have at the side of your desks, you've got 2 piles of little pieces of paper. You've got one that is filling in the gaps, like labelling the wave, and one that is a very simple question. So what I'd like you to do is have a go at labelling the wave first of all. And if you finish that, you can have a go, you can look at the question, have a go at the question too. But we will go through that question together. Yeah, just write on the sheet. Sorry. You can't close it fully, you can close it a little bit, but not fully. So we're looking for amplitude, wavelength, trough, and peak. Or crest and trough, sorry. Right. So I think you probably have enough time to fill in the gaps at least. So amplitude is from the zero position up to the crest. Trough is the bottom. Crest is the top. And wavelength is from one crest to the next crest. Okay, everyone get that right? Good. Okay. Right. Have a go at the other question. The other question's a little bit more tricky. So bear in mind all those definitions. So wavelength is the length of one wave only. The amplitude is from the zero position to the crest, or the zero position to the trough. And frequency is the number of waves in a certain amount of time. Okay, so first of all, the wavelength. Anyone think they know what the wavelength is? Yeah, Tom? How did you get that? Yeah. So as Tom said, we've got 4 meters in total, and how many waves have we got? That's 1, 2, 3, and 4 waves. Okay, 4 waves in 4 meters, so 1 wave is going to just be 1 meter. Okay, amplitudes. Yeah. Yeah. So 0.015, and where did you get that from? Yeah, exactly. Dividing that 0.03 divided by 2 is 0.015 meters. And what about the frequency? Yep, Daniel? Yep. Yeah. Excellent. Yep. Very good. Okay, so the first couple of pages of your question booklet are all going to be similar questions to those 2 questions. Okay, so you can make a start on those.